and welcome to part 2. We are going to look at something called retrosynthetic analysis. Something that's nice about synthesis is if you get stuck going forwards, try going backwards. In fact, sometimes working backwards is critical to setting up a good synthetic route. And you still need to be asking yourself the same 2 questions. Is the carbon skeleton changing? Is the functional group changing and or moving? You're still going to have to address those questions, right? But a lot of times a functional group in the product can help you design your synthesis. So for instance, let's take a look at this example that we have on the Klein slides. We're starting with this alcohol. We need to perform some sort of synthesis to get to this product. Now, is there a change in the carbon skeleton? No. We have 1, 2, 3, 4, 5, 6. And in the end, we have 1, 2, 3, 4, 5, and 6. Okay. Is the functional group changing or moving? Yes. It's not necessarily moving, but we are going from an alcohol to an alkyne. And so you may be able to start from the beginning and go to the end, and that would be great. But let's say you're struggling. You're not sure what to do with this alcohol just yet because you have different options. You can eliminate it. You can substitute it out. You can move it around. But let's say that you're not quite sure on your path to get to the alkyne. Well, then let's start at the end. Let's start here. Now, a retrosynthetic analysis is going to go backwards, and obviously it's called retro. Okay, sorry. It's going to use, oftentimes in this kind of an analysis, this big arrow. So I don't know if Klein uses it. Oh, yes, he uses it right here. This is very specifically saying we're going backwards. Now, you may start off with the wrong, in the wrong place. And I'm going to purposely make mistake here so that we can talk through it. There are several different ways that we could make this triple bond on this carbon skeleton. We need a dihalide and NaNH2. So where are those, where are those halogens going to be? So maybe at first you're thinking, okay, well, what if the bromines are both here? That would work, right? I could absolutely go forward and treat that with NaNH2 and get my final product. Okay, well then, how do I make that? Now, if I want to make a dihalide, the only way I know how to do it is from a triple bond, right? Is from adding HBr across a triple bond. Okay, well, hopefully we can see that that's not helpful. How can we make this product if we have to start with that product? So this was my first foray, right? Now I want to start over. Let me try this again. Oh my goodness. Let's draw this little starting material here. Or I'm sorry, not starting material, our product. And let's think about another dihalide we could use. The bromines can be on the adjacent carbons. It could be a vicinal dihalide instead of geminal. This is great because this gives us an intermediate that we could make from something other than the product, right? I know how to make a vicinal dihalide from an alkene, right? I can go backwards and use Br2. And then from that vicinal dihalide, I can use NaNH2. And now this is more of a plan that'll work, or that has potential, right? From here, now I just have to connect this guy, and I'm just going to go around in a little circle here. If I can figure out how to draw an arrow backwards. There we go. All right. Can I connect that to my alcohol? And when I do that, I should probably not lose carbons. All right, so I've got my little T-butyl group here. I have 1, 2 more carbons, and I have my alcohol. That is the starting material. I've just, for whatever reason, just twisted it around a little bit. Can I make this alkene from this alcohol? And yes, absolutely. What I could do is acid catalyzed dehydration, but I don't want to risk any rearrangements. So what I'm going to do is I'm going to use the TS chloride, right, the tosyl chloride. I'm going to make that into a good leaving group. Then I'm going to eliminate it in an E2 reaction that is not going to have any possibilities of rearranging. So I'm going to go ahead and use my potassium tert butoxide. Any of your strong bases would be fine here. Now, whenever I go to write this out, this is not how I want you to present an answer to me. This is the work, right? This is the work we put in. So from here, I'm going to go and I'm going to fill in these arrows, or, oh Lord, okay, I know that they've done it. I can either fill in the arrows, or I can list it this way, right? You notice they did the tosyl chloride. Pyridine, if you put it, great. If you don't, that's fine. Potassium tert butoxide, Br2. The CCl4 is just the solvent to make sure we don't do like a halohydrin formation. Then the excess NaNH2. I always forget this, and so I'm pretty relaxed with y'all if you forget it. Because it's a terminal alkyne, you need that water at the end. Otherwise, this carbon right here would be deprotonated. You'd make the same thing. It would just have a minus charge on it. This is how you would present the answer, either in a list like this, or kind of spelled out, starting material, first set of reactions, intermediate reaction, final product. Both would be fine. Now, I want to point out DBU, DBN, that's just another strong base. I'm glad they picked my favorite over on here, on this side. So this is one way you can work through a problem if, like I said, you get to a problem and you're like, oh my God, where do I start with this alcohol? There's so many things I can do. Well, look at the end. It's important to know where you're going before you plan your trip. Green chemistry is a great topic. It doesn't matter for us here. It is important in the world that we prevent waste, that we use less hazardous substances and safer solvents. Maximizing atom economy is important. You would want in real life to do a synthesis that was 5 steps versus one that was 45 steps. Definitely cost, time, all of just safety, all of those things are important. But right now, I want you to focus on just making a trip that works, right? Planning a route that works. If you give me a route that is 15 steps when there is a better route that's only 5 steps, if your route gets you there, you'll still get all the points. I promise you I'm not going to give you a problem that is going to have 40 steps, but you are going to come up with something I didn't think of. This is my favorite thing to teach, because no matter how many times I give similar problems, somebody always gives me a new right answer that I hadn't thought of before. So this really pushes your sort of like chemistry creativity. But I do not want you to worry about the green chemistry for solving these problems. Practical tips these are the same things, right? You have to answer these questions about the carbon skeleton or the functional group. So to answer those, to solve the problems, when you get a yes to those questions, you have to know the reactions. If you don't know the reactions, a synthesis problem is impossible, right? You have to know these reactions. So if you've been struggling with memorizing them and getting them down, you need to work on that. It's relatively easy to create your own synthesis problems, but I will give you plenty of problems to work with. I will put up a practice exam next week. You will have your synthesis lab, and you will have sapling homework that will absolutely provide you with more synthesis problems. For one way you can create them is to just start with something small and just start doing reactions that you already know. And then once you finish it, erase everything in the middle. Come back to it later. Notice multiple correct answers. Even Klein makes a whole section dedicated to this. There are multiple ways that we could go from A to B, right? We're adding water across this double bond. We could do that very simply, hydroboration oxidation. If you can't remember these reagents, though, you could still get this problem correct. If you treat this with HBr and ROR, right, you will get the anti-Markovnikov addition of that bromine. And then you could do sodium hydroxide and get a nice little SN2 reaction, replace the bromine with the OH. Both of these are equally correct. That's all 11 is. So hopefully something you've taken away from these two videos or from reading chapter 11 is that this is just kind of a how-to chapter designed to help you solve problems. It's not really giving you any new information in terms of reactions, stereochemistry, regiochemistry. It's just showing you how, okay, now you know these reactions. These are the kind of problems that we're going to ask you to solve. After you're done here, I recommend going and looking at the Synthesis 1 lab. There will be a video with it where I walk through a couple more problems. And I know I said this in the last video, can't emphasize it enough. I will check over your work before it's due with one little caveat, that you show me before the due date. Don't send it to me 5 minutes before Dropbox closes. But if you send me your synthesis that you're working on, I'm happy to look at it and give you feedback. All right, this is supposed to help you. This is a learning experience, and I want you to get better at synthesis before you have to sit down in a test and come up with one by yourself. Okay? I encourage you to work in groups if you can. Get in that course room and pull out your labs this week and work together. This is something that has been really important in previous semesters, is having those lab days. Make them yourself. Get on the phone with your pals, and work together if you can. Come to office hours and hang out with me. I'm happy to help you work.